Welcome to the OpenJ9 community call. If you haven't already, please add your name and company to the attendees list in the agenda. So our first thing on the agenda is a discussion of topics of interest to end users. Does anybody have anything they want to raise? Okay, today we have a talk by Dinakar about getting the most of your OpenJ9 Java app in a Kubernetes environment. So Dinakar, take it away.
Yep. Can you see my screen?
I can see about half of your screen for some reason, the left half.
Okay.
There, the rest of it's showing up.
Is that better?
Yeah.
Okay. So, okay. Let me get started then. So my name is Dinakar Gunigantala, and I'm the lead for the OpenJ9 Cloud Optimizations. I just wanted to talk about how to get the most of your Java application in Kubernetes with Eclipse OpenJ9. So today, as we all know, cloud is ubiquitous in both enterprise and startup environments. In fact, it is estimated that most enterprises today use a minimum of 5 different clouds across private, public, and hybrid cloud environments. So I wanted to specifically look into Docker and Kubernetes, which happens to be the de facto standard when it comes to cloud technologies today, and what does it mean in the context of Java. So if you look at the different life cycle, the application life cycles in the cloud, you typically start by building and packaging your application, and then deploying it or provisioning it in the cloud. And then you'd have to look at how quickly your application starts up in the cloud, and what are the inhibitors over there. And does it recognize the runtime, does it recognize the environment as per the restrictions that the cloud operates in? And there are some special conditions such as idle, which take into account the fact that clouds these days are priced on the basis of the memory that you're using, and what we can do with the runtime, in this particular context, and as well as look at some debugging aspects as well. So typically these are some of the application life cycles that a developer would need to go through. So let's take up the first one, which is essentially building and packaging and deploying to the cloud. Given that this is a lightning talk, I won't be going too deep into each and every one of these. And in fact, there are specific blogs that actually look at each of these in a little bit more detail. So what I would like to do here is to give you a brief overview on each of these, and then you can actually look up the blog and in some cases some YouTube videos as well for you to get more information on that. So if you look at the in the context of the build environment, what matters from a cloud perspective? Most of the time, provisioning time matters a lot. I've seen of cases where the provisioning, let's say, for example, it's happening to a public cloud, and you are on a very slow internet link. The size of the image matters a lot. So if you want to publish or provision to a public cloud over a very slow internet link, sometimes large images, for example, let's say if your image runs into something like more than a GB, then the times that it takes to actually push the image accordingly slows down considerably, or it takes a lot of time. And this not only affects provisioning, but if you want to, for example, if your cloud is spread across nodes or rather your workload is spread across different clouds and has to respond to transient conditions where you're required to spawn additional instances of your application across these clouds, then deployment times are one of the issues that you'd have to look at pretty closely. So what we are doing here in the case of OpenJ9 is to look at how do we reduce the size of the base Java image that your application is based on. And I've pointed a link down here so this is where you would get all of the images from the Adopt OpenJDK site. Again, I won't be going too deep into Adopt OpenJDK. I'm assuming that people are aware of what that is. So very briefly, Adopt is the place where you can grab Java binaries that are built as well as Docker images associated with those, and you can get both hotspot and OpenJ9 images. And the link at the bottom is where you would get the Java 8 OpenJ9 images. So if you look at the sizes that are mentioned out here for the different architectures, you can see that a full SDK would be around 330 MB in size. But something that is based on Alpine Linux, which is a minimal Linux variant, which is just about 5 MB in size, and having a JRE on top of which has been slimmed down specifically for the cloud workloads. It actually reduces the size quite a bit, and this we've seen that this actually reduces the Docker provisioning times by up to 40%. So the next thing that you would look at is, once you've deployed your application to the cloud, how quickly does the application start up? And here, again, you can use a couple of options. One is the X share classes. And we have, more specific examples out here in the, in the same link as given here below. So, I mean, very briefly, I have it here as well. So you specify Xshare classes, and this uses ahead of time compiled code. And so what you do is initially build the Docker image by running this particular command, Java Xshare classes, with your application. And once you bring up the application that actually builds the share classes, and it is also baked into the Docker image at the same time. And once you commit that particular Docker image, now you have a image that can that has the specific AOT classes that are related to your app. And so when you bring it up the next time, it actually reduces the startup times by up to 40%. And again, the specific steps for how to build the Docker image and bring it up is again available at the same link that I've shown you earlier. The other option that you'd want to look at is the X Quick Start mode. This has, I believe this has, and this results in a small amount of throughput loss. I think it's something like about 2%. But it is really good for short running applications, and a lot of the use cases that that do run in cloud environments today happen to be for short running applications. So this is something that you want to look at. So if you add both of these options in and run your containers, we've seen more than 40. Startup times reducing by more than 40%. And so this is not only applicable for startup, but also in the cases where you want to scale your application as well. It works equally in both instances. There are a couple of different ways of using share classes. The one that I just mentioned, where you are pre-baking your Docker images with the share class cache, is one of them. The other one would be for you to be able to use shared volume, which is shared across all the containers running on a given node. and have the shared class cache available on that node as well. So both of these examples are available on the hub.docker site, and steps on how to use them as well. The next thing that you would want to look at is, when your application is running, what are the issues that you would face typically in the cloud, and how are there any tunables available to get the most out of it. So if there's one thing that you would want to get out of this presentation, I would say that it is the use of -XX max RAM percentage instead of -XMX and XMS. So typically Java programmers tend to use XMX and XMS, and this most of the times happens to be baked into the scripts which launch the application. What I would like to say here is that please don't use that, or at least review the use of these variables going forward in the cloud. So the reason for that is XMX and XMS happen to be non-container aware. So when the JVM comes up, it typically looks at the system, the system-wide memory and the cores that are available across the system, and so base the decisions of the XMX and XMS based on that. And the other aspect is that Kubernetes typically runs in a in a dynamic way, in the sense that so you can have the same application running with, let's say, lesser amount of memory, lesser amount of memory given to a container, and for certain use cases, and the exact same Docker image having the exact same application being given more memory in certain cases. So you'd have the same application with more memory in certain cases and less in certain other cases. So XMX and XMS might not be the best way to tell the application how much of a heap to use. So what you would be using is -XX max RAM percentage instead, which would look at the container restrictions, if any. So you can specify in Kubernetes to say that I want, let's say, 2 GB of RAM available to a particular container, or you can say 512 MB or whatever it might be. So max RAM percentage would then look at the container restrictions and base the heap size on the on the container restriction rather than the system-wide memory that's available. Similarly, initial RAM percentage is the equivalent of -XMS, and that would help you to get the most out of the container as well. One thing that most typical cloud environments do is that they run only one application per container. It's called as one responsibility per container, and that means that you want to make sure that you're using up as much of the heap that is allotted to the particular container as possible. We've already set the default settings to be 75% of the container restriction as the heap size today. If you want to tweak that, you can use max RAM percentage to, let's say, for example, make it 90%, or let's say 50% for whatever reason. And also try and set the initial RAM percentage to the same amounts, because you anyway have certain amount of the heap associated by Kubernetes to the specific container. You might as well make use of all of it. So those are the couple of options that you want to take a look at. There are some other, number of other container specific optimizations that have been done. I believe that Ashu has already given a talk in the same forum earlier. There's also a blog that Ashu has written, and that's there. The link is there at the bottom. The other aspect, again, which is talked about in a number of forums, is that OpenJ9 consistently uses the lowest memory footprint as compared to other JVMs out there. And we've seen that we can pack a lot more number of containers for the same available physical memory. In this case, for example, if you have 8 GB usable memory, we can actually pack in 16 of OpenJ9 application instances, as opposed to what 5 with OpenJDK and Hotspot. So this roughly translates as more than 200% more instances for the same set of resources. So these kind of calculations really matter when, let's say, for example, you have AWS instance, T2.micro or something that you have provisioned on AWS, and you want to make sure that you're using the given resources to the maximum. Then you need to look at how do you want to carve up the entire memory that is associated with that particular virtual machine on the public cloud or even in your private cloud, and accordingly associate the memory associated with individual containers. And OpenJ9 automatically the two aspects that I've mentioned out here in terms of using the max wrap percentage and the fact that OpenJ9 uses the least amount of memory footprint allows you to make the most of your resources in the cloud. The next thing that we have is idle. So what happens when your application is idling? And this again is significant in the cloud or in certain clouds, because if I take the same example as I did earlier in terms of using AWS, for example, there, or even in Bluemix, where you're paying for the amount of memory that you're using. So there are a number of charging models, and memory is one of them. And if it so happens that you're using that, then you need to be conscious of the amount of memory that your container is using at any given point in time. So since you're charged based on actual usage, what we have now as a feature in OpenJ9 is that it would detect, first of all, whether the application has gone idle, and reduces both the CPU and memory usage on idle, so that it doesn't matter if you're being charged on the basis of CPU or memory, you would be charged less. And there are certain okay, sorry, I was on the wrong slide, but this is for idle. So there are a couple of options: idle tuning, GC on idle, idle tuning compact on idle, but both of these are actually pre-baked into the adopt Docker images, so you don't need to actually set these. And the same is the case with the container awareness as well. So they have been actually pre-baked. In fact, container awareness is now the default, I believe, in the latest OpenJ9. So you wouldn't have to worry about it anyway. So all you need to do is just Docker pull the latest set of images, and these options would be turned on by default. And so you would get the benefits of these features anyway. So this was the other slide that I was wanted to take a look at in terms of OpenWhisk did a sort of an independent evaluation of all of the features that I was just talking about, specifically for the OpenWhisk case. So OpenWhisk, as you may be aware of, is the serverless. The serverless environment that is that IBM is contributing to, as well as supported in our cloud. So it's also a open source project. It's under the Apache Foundation, and so you can take a look at it. It's available for you to be able to set it up and test and so on. So this is the serverless platform where you can set up actions for, let's say, you have certain events which act as triggers, and then you want to set actions based on those triggers, which essentially are nothing but snippets of code. And Java is one of the actions that is supported in this environment. And so it has a specific set of constraints in terms of being able to start up pretty quickly and act on that request, because users are only paying for the amount of time that the request is serviced. And so it really is important for the system overheads to be as low as possible when the action needs to be serviced. So the startup needs to be pretty quick enough, and again, we don't want any kind of the lack of container awareness or environment awareness coming in disturbing the while the action is being executed, as well as make sure that given that a number of concurrent such kind of actions need to be executed at the same time, you don't want to make sure that the footprint is small enough that you can pack in a number of these at the same time. So this is actually a very good use case for all of the optimizations that I mentioned earlier. And they are using OpenJ9, and you can take a look at some of the benchmarking as the results of that that we looked at earlier on, and the link for that particular blog is mentioned out here. Did forget to mention that there's a blog for idle awareness as well, and take a look at the link out here. And the last thing that I wanted to mention was in terms of debugging. So debugging is, of course, something of a concern for all of the developers, especially in a new environment such as cloud, where you don't know where exactly your container is running and not really sure how to gather debug information of your containers. So one of the things that we have looked at is to add a MX bean. It's the OpenJ9 diagnostic MX bean. It's actually a link. You can take a look at that. So what this bean does is it has a number of methods as listed out here that help you to trigger a dump and set the path where the dump needs to be taken. So both of these help in cloud environments because for example, when you're running up your application, you typically would want to have logging volume associated with that as well. So for example, if you're running, let's say, Liberty or JBoss or Tomcat application, all of the logging needs to be captured into, let's say, either a container volume that's a Docker volume container, rather, that is associated with that, or maybe a path, that's, and let's say, for example, an NFS volume, or any of the other supported storage volumes that are associated, that are across all of the containers that need to be running. One thing that most of the containers are that they are stateless, and so they wouldn't have any information by themselves, and all of the information is pushed outside of the container to logging volume, as I just mentioned, which is outside of that and is just mounted by Kubernetes when it constructs or runs the container. And so when we are trying to take a dump, we want to make sure that you're dumping to one of these volumes that are already associated with that particular container that is running. So once you get to know, let's say, for example, you have a number of containers that are running. Once you have a failure or one of the containers that is having you notice that it's either dying repeatedly or having some issues. You can log into any one of your other Java instances, the application instances that are running in, and then set some dump options based on the methods that might be causing these issues, and say trace on this, or or rather, sorry, dump on such and such a error condition and so on. So you can set those dump options and say that you trigger it to this particular file on this particular volume or path that is associated with that particular container. And if you do that, you should be able to get the dump next time the application crashes. And because you have access to that volume, you should be able to then use your normal debugging tools and utilities to take a look at what's going on. There is a blog associated with this, and it does go through in some detail in terms of step-by-step instructions on how to do this, and there's also a YouTube video that talks about this as well. These are some of the links that generic links that I'm sure the folks on the call here are already aware of, but just wanted to make sure that this is available for completeness. That's pretty much all I had. So any questions?
Thanks, Dinakar. We'll get this video put up on YouTube so everyone can take a look at that.
Yep.
Given that we're out of time, I think I'll just stop the call now, unless anybody has any other urgent business they want to discuss. No? Okay. Thanks, everyone.
Yep. Thanks, Peter. Thanks for setting this up.
Yeah, thanks, Dinakar.
Thanks.